In this video, I'm going to continue talking about light, energy, frequency, wavelength, and finally tie this in with the atom and electrons. So if you look at these pictures here, this is showing you how white light is made of all the colors of the spectrum. White light is one of those continuous spectrums that we talked about. If you took white light, passed it through a prism, you would see all the colors here, the Roy G. Biv, and there would be no gaps or breaks. If you did this with colored light, though, you would only see certain wavelengths. So it's going to be a non-continuous spectrum. If you did this with a helium lamp and passed it through a prism, notice you only see certain lines present, and there's actually gaps. So that's an example of a non-continuous spectrum. This brings us to this idea of an atomic emission spectrum. This is when you only see certain colors or wavelengths. Every element gives a unique pattern here. So every element gives its own specific pattern here when you do this. We call this an atomic emission spectrum. It's not going to be a continuous spectrum. You're not going to see every color blended one to the next. There's going to be gaps here or breaks in this. So the basic gist of what happens here is this. When you add energy to an atom, so heat it up, put it in the fire, add electricity, you are exciting the electrons. So the electrons get excited and they go from a ground state, which is lower in energy, to an excited state, which is obviously higher in energy. So picture the Bohr model, an electron in a lower orbital, you're giving it energy, so it gets excited and it jumps up. Well, just as quickly as it goes up, well, what goes up comes back down. But when that electron comes back down, it has to give off some of that energy, okay? And as it gives off that energy, some of that energy is in the form of visible light that we can actually see. So some of that energy has a frequency here proportional to that energy change. So just to recap here, if you have an atom, you excite it, you give it energy, the electrons go up to a higher energy level, and just as fast as that happens, they drop back down, and in the process, they give off energy, and some of that energy is in the visible light region that we can see. So they get excited, they jump up, they fall, and they give off energy in the form of light. So if you look at some of these atomic emission spectrum for different elements here, you can see the top one here is for sodium. Notice sodium really only has one line there. It's kind of in the yellowish orange region. If you were to see a sodium street lamp, they give off like an orangish yellow color. I think many of the street lamps now are switching over to LED, so you don't see this as much, but many of the older street lamps were this orangish yellow color because they were using sodium lamps. So you can see there's some atomic emission spectrum there for different elements. Notice they are not continuous. You only see certain colors or wavelengths. So you need to understand this idea that every element's going to be unique. And when you add energy to an atom, the electrons get excited and jump to a higher energy level. They fall back down just as fast and they give off energy in the form of light. And we can actually look at this energy and do some calculations with it. Before we do the calculations, people always say, well, why is this important? What is this? What does this even matter? Well, this is how neon lights work. All right. So you put certain elements here, certain gases in the neon light tubes. You plug them in. So you're adding electricity. You're exciting the electrons. They go up, they fall back down, and they give off energy in the form of light that you can see. Neon lights are not all filled with neon, or they would all be the exact same color. Neon is very similar to this color here. So obviously, if all neon lights were filled with neon, they would all glow the same color. But this uses this idea here. This is also how fireworks work. If you want to have, different color fireworks, you switch out the elements here in the fireworks. If you want a green firework, you use something like barium. If you want more of like a red firework, you're going to use like strontium or lithium. So it's the same idea. When you burn these elements here in the fireworks, the electrons get excited, they jump to a higher energy level, they fall back down just as fast, and they give off energy in the form of light that you can see, and it has a pretty color, and you enjoy the fireworks. Now we have a second equation that we can use for these problems. We already know that C equals wavelength times frequency, but now we can tie in energy here. So E equals HV. E is going to be the energy. It's going to be in joules. H is another constant. It's Planck's constant, 6.63 times 10 to the minus 34th joules times second. It's just like C. That's the value it is all the time. We will give you H, so you don't need to memorize H. You do need to know C, but you don't need to know H here. You'll be given that. And then again, remember, it's not a true V. It's actually a Greek letter here. That's frequency, and you need frequency to be in hertz. So what we can do is you can take these two equations, solve the C equals wavelength times frequency equation for frequency, and then plug that into this E equals HV equation, and you get a third equation, E equals HC all over wavelength. So now we have three equations that we have to worry about. So when you're approaching these problems, you do have to consider, all right, which of the three equations do I need to use now? And I'll show you how to approach these problems in the examples we're going to do. This first example says, what is the energy of blue light with a wavelength of 3.60 times 10 to the negative 8th meters? So as I said, now we have three equations that we have to worry about. So I recommend starting all these problems this exact same way now. The first thing you need to do is figure out which equation you need to use. So the three equations we need to know are C equals wavelength times frequency, E equals HV, and E equals HC all over wavelength. Okay, so now what you need to do here is figure out what is the problem asking me for and what am I given. So in the problem, we want to know what is the energy. So immediately, one of these three equations can be eliminated. If we're solving for energy and an equation doesn't have energy in it, we can cross it off. So if we're solving for energy, the top equation we're not going to use. We know immediately that equation is not going to be used because it doesn't have energy in it. And then the problem gave me wavelength. So which of the two remaining equations has wavelength in it? Obviously, it's the last one. So that's the equation we need to use. That's how you approach all of these problems from now on. You have three possible equations, see what they're asking you to solve for, eliminate an equation that doesn't have that in it, and then see what the other thing they gave you was and which of the remaining equations you need to use. So now I know I must use E equals HC all over wavelength here. So I'm solving for energy, so that means I'm just going to plug in my numbers here and solve for E. So H is a constant. Remember, it's always 6.63 times 10 to the minus 34th joules times second. You will be given H. C you need to know is the speed of light. That's 3 times 10 to the 8th meters per second all over wavelength, which the problem tells me is 3.60 times 10 to the minus 8th meters. Remember, you do want wavelength in meters. You must have wavelength in meters here. If it wasn't in meters, you'd have to convert. So this is just, doing the math here and solving. So multiply your two numbers on the top, hit equals, get an answer, and then divide by the 3.60 times 10 to the minus 8th in parentheses. You're dividing by an exponent, so if you don't put it in parentheses, you won't get the correct answer here. So now you are solving for E, so you're solving for energy, so you should know your units should be in joules. You do have to pay attention to sig figs, so go back to your original problem here. Again, all you're doing is multiplying and dividing, so count sig figs and use the least, so it's going to be 3. So when you solve this, your energy with correct sig figs and units should be 5.52 times 10 to the minus 18th joules. Your units here are going to be joules. If you didn't get the right exponent, you didn't plug it into the calculator correctly. Make sure you can plug this in. So now that's pretty much how you're going to approach all of these problems. Figure out which equation you're going to use, plug in, watch your units, and solve. We can try one more example here. This one says, what is the frequency of the photon from the previous problem? So Again, you're going to approach all these problems the exact same way. You have three equations to worry about. C equals wavelength times frequency, E equals HV, and E equals HC all over wavelength. You need to know what the equations are. You need to know them. You need to know what the letters stand for and what units they should be in. That's the first step. If you don't know the equations and you don't know what units these things should be in, that's where you need to sit down and study first. So this problem says, what is the frequency? So if I'm solving for frequency, I immediately know this third equation can be eliminated because it doesn't have frequency in it. So that equation is gone. So now I have two equations remaining here. I have the C equals wavelength times frequency, or the E equals HV. Based on the information in the previous problem, they gave us the wavelength and we solved for the energy. So in theory here for this problem, because it's based off of the other problem, I solved for the energy in the previous problem. So I could use this equation because I now know the energy and I'm solving for frequency. But they gave me the wavelength in the problem, so I could use this equation as well, because now I know the wavelength because it was given, and this is a constant, so I could solve for frequency. I'm going to opt to use this first equation because let's just say I calculated the energy wrong in the previous example. That would make this problem wrong as well. I know that the wavelength is correct because they gave it to me, so I'm going to use that number here. So I'll use the C equals wavelength times frequency, but in reality, I could have used E equals HV as well. But that's how you approach all of these problems. Look at the three equations, figure out based on what you're solving for and what you're given, which of the three equations you need to use. It's a process of elimination. So now I'm going to plug in here what I know. C is 3 times 10 to the 8th meters per second equal wavelength. We said the wavelength from the previous problem was 3.60 times 10 to the minus 8th meters. Do we want meters here for wavelength? Yes, you must have the wavelength being in meters to be able to use this equation, times frequency, which is what I'm solving for. So you're just going to divide both sides by the 3.60 times 10 to the minus 8th. You're solving for frequency here, so your units are going to spit out hertz. If you're solving for frequency, your units are going to be hertz as long as your wavelength was in meters. You do need to watch your sig figs. Make sure you can do the math here. It should come out to be 8.33 times 10 to the 15th hertz for frequency. All right, so that's how you're going to approach all these problems from here on out. Know your three equations, know what the units should be, and just figure out which of the equations you need and then plug in and solve. The last idea we're going to talk about in this video is Heisenberg's uncertainty principle. Heisenberg's uncertainty principle basically says you can't know both the speed and location of a particle at the same time. So you can't know the velocity and the position of a particle at the exact same time. This doesn't apply to large objects. All right, it's not like you're going to see a car going down the street and be like, well, I see it, there it is, but I don't have any idea how fast it's going. Or, I can see how fast it's going, but I don't know where it is. No, this only applies to really, really small objects like electrons because they are so light. All right, they're so small that when you try to figure out information about their velocity or their position, you kind of cause it to change speed or change position in the process here. So that's what we're going to look at on the final slide here in a second. So this only applies to really small objects. So what this picture is showing you is we're trying to figure out information about this electron right here. So we use a photon or some form of energy or light here to get information about this electron. So when this photon comes in and hits this electron, right, the minute it hits, that photon will change and come back and give us information about that electron. But because the electron is so light, the electron now changes its velocity or changes the direction it's going. So even though we were trying to get information here about the electron, in the process of doing that, because it's so light, we actually changed it. So we can't know both the speed and location of a very small particle like an electron here at the exact same time, just because they're so small. And that's basically what Heisenberg's uncertainty principle says.